Hello, we are working on 6.3c, geometric random variables. And as I mentioned, this is actually the easiest of the two types of random variables. So I'm very excited to talk to you about it. Let's consider the game of Monopoly, where if you want to get out of jail, you can do that by rolling doubles. So in the board game Monopoly, one way to get out of jail is to roll doubles. How likely is it that someone in jail would roll doubles on his first attempt? What about his second attempt or his third attempt? If this was the only way to get out of jail, so you couldn't get out of jail just by going through the turns, how many turns would it take on average? We can describe this scenario using a geometric random variable. And just like a binomial random variable, there are a few characteristics of a geometric random variable, and it has the acronym BITS. So a geometric random variable has the following characteristics. Notice it has three of the characteristics that are exactly the same as a binomial random variable. It's binary, which means it can either have a success or a failure. The trials are independent. Trials don't influence one another. And notice the probability of a success is the same for every trial. Probability of a success is the same for every trial. The only thing that is different is not bins, where n, the number of trials, is fixed, but it's bits, where the word in question is trials ? Meaning the difference in a binomial random variable and a geometric random variable is in a geometric random variable, we are counting the number of trials until a success. So let's look at another definition. The number of trials y that it takes to get a success in a geometric setting is known as a geometric random variable. The probability distribution of y is a geometric distribution with the parameter p, which is the probability of a success on any trial. The possible values of y are 1, 2, 3, and then ... meaning it goes on forever. So think about this. If I say y is the random variable we talked about like rolling doubles, and it's not I'm rolling 5 times, it's how many times do I have to roll 2 dice until I actually roll doubles. So I would roll, if I get a success on the first roll, then I'm done. But maybe it'll take me 2 times to roll doubles, or maybe it'll take me 3 times, or maybe I'm going to fail, let's say 10 times before I actually get doubles. This is a geometric random variable. It's rolling until I get these doubles, or failing until I succeed. So geometric probabilities, or I guess we will look at the Monopoly example. The random variable of interest in this example is y, the number of attempts it takes to roll doubles 1 time. Each attempt is 1 trial of this chance process. Let's check the conditions for a geometric setting. We kind of just talked about it, but we can real quick go over it. B, it's binary. Either I roll doubles, a success, or I don't. I, independent, because of course, rolling a dice is independent of every trial. T, I am not setting a number of rolls, but I am counting the number until I succeed. The number of attempts it takes to roll doubles. And then last but not least, S, the probability of a success is the same every time. We know the probability of rolling doubles is 1/6. Geometric probabilities. If y has a geometric distribution with probability p of success on each trial, the possible values of y are 1, 2, 3, etc. And if k is any one of these values, then the probability that y is equal to k is equal to 1 minus p to the k minus 1 times p. Pause the video, write this down, but let's talk about this, because realistically, this is not a challenging formula. If I want to find the probability that I succeed on my third roll, that means I'm going to fail, and then I'm going to fail, and then I'm going to succeed. So I would take the probability of a failure, which is 1 minus the probability of a success, and there's 2 copies there, to the k minus 1, so squared, times the probability of a success. That's what this is saying. 1 minus p is the probability of a failure. P is the probability of a success. I am succeeding on this last trial, and I am failing every trial except for that last one. Now, very important note is that guess what? This formula is not on your AP formula sheet. However, don't stress. This can be found just using our general multiplication rule and complement rule for independent events, right? Because we know these events are independent, if I want to find the probability that I fail twice and succeed on the third, I'm going to fail and succeed. It's the probability of A and B, where A and B are independent events. So it's really just that general multiplication rule. Let's try a problem. Let the random variable y be defined as the previous example. It says find the probability that it takes 3 turns to roll doubles, and then find the probability that it takes more than 3 turns to roll doubles. For A, here's what we know. Y is the number of rolls it takes to get doubles. So either I can succeed on my first, or my second, or my third, or my fourth roll. Y can be any of those numbers. I know that the probability of a success rolling doubles is 1/6. So if I want to find the probability that I get a success on my third roll, it takes 3 turns to succeed. So I get a success on the third. That means I'm failing, and succeeding. So in this case, I'm going to fail twice. 5/6 squared, and then I'm going to succeed once, times 1/6. If you take those 3 fractions and multiply them, you should get 0.1157. And it shouldn't shock you that, of course, there is a calculator command for this. This would be geometric PDF, not CDF, PDF, because it's a particular value. It is one specific PDF. And in that calculator command, it asks you for the probability of a success, 1/6, and the trial number, so that would be 3. Double check your work, but you should get this 11%. Then B says, what is the probability that it takes more than 3 rolls to roll doubles? Okay, this one's a little more complicated. The probability that y is greater than 3, more than 3. Well, the catch is that could be the probability that I get 4, or it could be the probability that it takes me 5 rolls, or it could be the probability that it takes me 6 rolls, or realistically, it could go on forever. So instead of finding all of these probabilities, of course, we're going to use our good old complement rule. So the probability that y is greater than 3 is equal to 1 minus the probability that y is less than or equal to 3. And this we can either find by finding the probability that y is equal to 1, y is equal to 2, or y is equal to 3, and adding those 3, or probably the better option would be to use our geometric CDF for cumulative, where the probability of a success is 1/6, and the value we are curious about is x equals 3. Remember, cumulative is going to give us everything less than that. And both these commands are in the exact same place as binomial CDF and PDF, so second vars. If you want to pause the video to find your calculator and calculate this problem, otherwise you should get 57.87 if we made it a percent, or 0.5787 as a decimal. There's a 58% chance that it will take me more than 3 turns to roll doubles. Got reminders of the calculator commands. We already kind of looked at this. Particular, meaning a specific value. C, cumulative, meaning everything less than or equal to. The probability that y is equal to k, or the probability that y is less than or equal to k. Cumulative, particular. And then the last thing in this section is a really small, and hopefully it makes sense, example. The mean, or expected value, of a geometric random variable. The mean, otherwise known as the expected value, is equal to 1 over p. So let's take a moment and think about this. P is the probability of a success. In our last example, the probability of rolling doubles is 1/6. Now we know that a probability is a long-term frequency, right? It really only approaches 1/6 if I do this many, many, many times. But if it's acting perfectly, we would expect to roll doubles. If it happens in 1 out of 6 rolls, we would expect it to happen 1 over 1/6. We would expect it to happen in about 6 rolls. If there's a 1 in 6 chance of it happening, I'd expect it to happen in those 6 rolls. If you don't, never mind, I'm not going to say that. Thank you for staying with us. We are technically done with 50% of the content in this class, so pat yourselves on the back. Let me know if you have questions on the homework, and I will talk to you soon.